So this is a video quiz with 4 questions. They are integrals which can be tackled through a variety of techniques, and the aim of the video is to give you the opportunity to practice pattern spotting to work out what is the appropriate technique and then to calculate the integrals. So I suggest you write these integrals down on pencil and paper and then try to calculate them. Do not look at the rest of the video until you've done that, and then what you can do is you can go on to the next slide in this video and see whether you've got the answers right or not by pausing and just looking at the answers, and then if there are any of them that you have not been able to do, the answers are contained in the rest of the video. So I suggest you now pause the video, write down the questions and calculate them. Okay, welcome back. Let's go on to the next slide and look at the answers. So here are the answers to the 4 integrals, and one of them was a definite integral. So I've written down the answer for the indefinite integral and then the result that one would obtain overall. And if you have got any of these integrals wrong, what you can do is go through the answers in detail on the next slides, and then perhaps at a later stage come back and try to do the video again. So you can pause and just check the answers in detail. Okay, welcome back. Let's move on and look at the remaining answers and how they were calculated. So this integral initially looks quite complicated because of the square root of 1 minus x cubed, but outside is a factor of x squared, and x squared is up to a number, the derivative of 1 minus x cubed, and that makes this a straightforward integral that you can calculate either by making a simple substitution or by inspection. And what I'm going to do here is calculate the integral by inspection. And to do that, I'm just going to rewrite it in the following way. I'm going to leave a little gap in front of the integral sign. I'm going to write minus 3x squared. I'm then going to write the square root of 1 minus x cubed integrated with respect to x, and I've put in a factor of minus 3 by hand, so I have to put in a factor of minus a third as well to ensure that I've not changed anything. And now we see that the way this has been written, this is exactly the derivative of the content of the square root. The square root is 1 minus x cubed to the power of a half, and a function that would give us 1 minus x cubed to the power of a half, if we differentiate it, could be 1 minus x cubed to the a half plus 1 to the 3 halves. So let's see what happens. So we have minus a third, and I'll leave some space, 1 minus x cubed to the 3 halves. Now, if we differentiate this, we will pull a factor of 3 halves in front, and we don't have a 3 half factor here in the original function, so I'm going to write 2/3, so that will cancel the 3 halves. We would then reduce the power by 1 to a half, and that is exactly the square root factor, and then from the chain rule we would multiply by the derivative of what's in the bracket, and that would be minus 3x squared. And minus 3x squared was in the original integrand, and that factor of x squared here or here is what made this a very doable integral. So if we differentiate this, we get exactly this, so we have completed the integral. So therefore let's just tidy things up. So we have the integral of x squared square root 1 minus x cubed integrated with respect to x is minus 2/9 1 minus x cubed all to the power of 3 halves plus an unknown integration constant. And that is our answer. If you wanted to calculate this through a simple substitution, the best way to do it would be to say that your new variable, whatever you're going to call it, you say, would be 1 minus x cubed. But I think the easiest way to do things like this is just by inspection. So let's move on now to the next integral. So this integral could be calculated in a couple of different ways. We see the square root of 1 minus x squared here, and we might think about trying a sign substitution, and that indeed works. However, I think it's somewhat simpler if we recognise that because of the x cubed factor here, we can also write this as the integral of x times x squared times the square root of 1 minus x squared, all integrated with respect to x. And I can write that suggestively as the integral, I'll leave a bit of space, x squared square root 1 minus x squared, and I'm going to put in brackets minus 2x integrated with respect to x. So I've inserted here a factor of minus 2, so outside I'm going to put a factor of minus a half, and now I have not changed anything. Now this looks like a case where simple substitution might help. So this would be our new variable, this would be what we can call u. This is then going to be a factor of 1 minus u, and here, if this was u, this is the derivative of u with respect to x. So let us say that u is 1 minus x squared, and that means we can write x squared is 1 minus u. So all of our integrand is written in terms of u quite easily, directly, and this factor here is going to be du dx, because the derivative of u with respect to x is equal to the derivative of 1 minus x squared, so it is minus 2x. So again, all we have to do is to recognize that this integral that we are trying to calculate fits the pattern of simple substitution. In other words, we recognize that our integrand that we have here, or here, is of the form that it is written in terms of u, and we see that everything here can be re-expressed in terms of u, and that we have this factor of du dx, and in that case we just have to integrate everything with respect to u, and we can then at the end rewrite u in terms of x using our definition here. So what we see is that our integral, the integral of x cubed square root 1 minus x squared with respect to x, is minus a half, that's the factor here, and then we have x squared times the square root of 1 minus x squared, so that's 1 minus u times the square root of u. So this is the integral of 1 minus u in brackets multiplied by the square root of u, now integrated with respect to u. So again, we just expand this. This is minus a half, the integral u to the 1/2 minus u to the 3/2, all integrated with respect to u. So what we obtain is minus a half multiplying, and now we have got two integrals, this integral and this integral, and to integrate u to the half we add 1 to the power and then multiply by the reciprocal of this new power. So we have u to the 3/2, and then we multiply by the reciprocal, so that's a factor of 2/3, minus, and now it's u to the 5/2, 3/2 plus 1, and then we multiply by the reciprocal of 5/2, so that's a factor of 2/5, and then let's close the brackets and add an integration constant. So we can now expand this and tidy up and write our final answer. So the integral of x cubed square root of 1 minus x squared with respect to x is going to be, so it's minus a half times 2/3, so that's minus 1/3, and u is 1 minus x squared, so this is 1 minus x squared all to the power of 3/2. And now minus minus becomes plus, minus sign here and here, and the 2 and the 2 here are going to cancel, so we're going to get plus 1/5, and u is 1 minus x squared to the 5/2 plus an integration constant, and that is our answer for this integral, which may be checked by differentiation. That's a good exercise. So, as said, we could also calculate this integral using a sign substitution, and it's simply this factor of x cubed that made us think about using a simple substitution. If we had the integral, say, of x squared times the square root of 1 minus x squared, this would not work. We would not so easily be able to do this method, and we would be much better off using a sign substitution. So we have to look at the form of the integrand and try to spot the best pattern. So let's stop and move on to the next integral. So our third integral is the integral of the cube of the secant function. And whenever you see powers of the secant function, the two following things should be in your mind. One of them is that the derivative of the tangent function is the square of the secant function, so the integral of sec squared is tangent, and the other is the identity that sec squared theta is 1 plus tan squared theta. And this is obtained just by saying that sec squared is 1 over cos squared, and if you write the 1 in the numerator as sine squared plus cos squared, this drops out. So those are the two key things that should be in our head when we look at this. So let's now think about how to do this. So our integral is the integral of sec cubed theta, and all of our identities involve sec squared. So let's write this as a product of sec squared theta and sec theta with respect to theta. So we could immediately rewrite sec squared here as 1 plus tan squared. The integral of sec is a straightforward integral. It's a standard one that we can learn. And then we'd be left with the integral of tan squared times sec, and that's perhaps not immediately obvious. So instead of that, what I'm going to do is to look at using integration by parts. So I have here a product. Integration by parts is quite natural, and I have to now choose which factor I want to differentiate and which factor I would like to integrate. And the factor I would like to integrate is sec squared. So I want to integrate this factor here, and that means I'm going to call this v prime, and this factor here I'm going to call u, and I will differentiate it. So what we're going to do is to recall the integration by parts formula, that the integral of u v prime with respect to a variable, here theta, is uv minus the integral of u prime v integrated with respect to our variable. So that's our formula. U is sec theta, so u prime, the derivative, is sec theta tan theta, which you can calculate from scratch, but it's easier if you know it. And v prime, the derivative of v, is sec squared theta, and that has that very nice integral that the integral of sec squared theta is tan theta, because the derivative of tan theta is sec squared theta. So now we take these results, put them into this formula, and that will give us a result for the integral. So let's call the integral I, and it is u times v, and u is here and v is here. So this is sec theta tan theta minus the integral, and now u prime is sec theta tan theta, and that was u prime, and v is tan theta, so this becomes tan squared theta. We have a tan theta from the derivative and another tan theta from the integral, so we have overall sec theta times tan squared theta integrated with respect to theta. So far in this question we've used this to be able to integrate sec squared, and now we see a factor of tan squared and we think about this identity, because tan squared theta is sec squared theta minus 1. So our integral is going to give us, well, we have sec theta tan theta minus the integral of, so sec theta times 1, that's the integral of sec theta, and then tan squared theta is sec squared theta minus 1, so it's sec squared theta, well, let's write it out slowly, it's sec squared theta minus 1 integrated with respect to theta. So we have sec theta tan theta minus the integral of sec cubed theta with respect to theta, plus, because of the two minus signs, the integral of sec theta with respect to theta. Now, this is a standard integral, and this is our initial integral that we've called I. And it's got a minus sign here, so I can add I to both sides. Here I will get 2I, and here I'll get rid of this. I'm just taking this over to here. So this tells us that 2 times our initial integral is sec theta tan theta plus, and now the integral of sec theta is the logarithm of the modulus of sec theta plus the tangent of theta, close the modulus. And this is our result, and all we have to do now to obtain the final answer is divide both sides by 2 and add an integration constant. But I will stop here and move on to the next slide to look at the final integral. So this integral is a definite integral, and it involves the cosine of our variable to the power 4. And the key thing to notice is that this is an even power, and as soon as you see an even power you should think about the following identity. The cosine, the double angle formula, the cosine of 2a is 2 cos squared a minus 1. And if we had sine to the power of 4, then you would say cos of 2a is 1 minus 2 sine squared a. But this is cosine to an even power, so this is our key formula. So this can be rewritten, and it tells us that cos squared a is 1/2 brackets 1 plus the cosine of 2a, close brackets. So in particular, for us, cosine squared of 2 lambda is 1/2 1 plus the cosine of, and now it's 2 times 2 lambda, so that's 4 lambda, close brackets, close brackets. So this is our result for cos squared, and cos to the power of 4 is cos squared squared. So cos to the 4 of 2 lambda is 1/2 1 plus the cosine of 4 lambda, close brackets, all squared. So that is 1/4 because of the half squared. And now we just multiply this out. 1 squared is 1. The cross terms are going to be 1 times the cosine, but there will be 2 of them, so it's 2 cos 4 lambda plus cos squared of 4 lambda, close brackets. So looking at this, integrating 1 is easy. Integrating the cosine of 4 lambda is also standard, and integrating cosine squared of 4 lambda, well, why don't we go back to this identity and use it again, but now with a being 4 lambda, so 2a will be 8 lambda. So in that way we see that cos to the 4th of 2 lambda is 1/4. 1 plus 2 cos of 4 lambda plus, and now it is 1/2. We're just using this formula, that's the half, brackets 1 plus the cosine of 8 lambda, close brackets, close brackets, close brackets. So now we might as well tidy this up a little bit. It is 1/4, and here we have a 1 plus 1/2, so that's 3/2, plus 2 cos 4 lambda plus 1/2 cos of 8 lambda, close brackets. And now we have rewritten our integrand in a way where every term can be integrated. So therefore our integral from 0 to pi of cos to the 4th of 2 lambda with respect to lambda is the integral of all of this. I can take the half outside, so not the half, the quarter outside, so this factor of 1/4 can come out, so it's 1/4. It's the integral from 0 to pi of 3/2 plus 2 cos 4 lambda plus 1/2 cos of 8 lambda, close brackets, integrated with respect to lambda. So this is 1/4. Now we'll open big square brackets. The integral of 3/2 with respect to lambda is 3/2 lambda, and the integral of cosine is sine, so we're going to write the sine of 4 lambda, and if I differentiate that I will get 4 times the cosine of 4 lambda, and I want to have a factor of 2, so I'd better put in plus 1/2. And then here in a similar way I want the sine of 8 lambda, and if I differentiate that I will get 8 times the cosine of 8 lambda, and I have a factor of 1/2 here, so I'd better put plus 1/16. Now close my brackets, and this is to be evaluated between 0 and pi. And before we go into the gory details of doing it, let's just realize that everything here vanishes at the lower limit. When lambda is 0, that vanishes, sine of 0 is 0, sine of 0 is 0, and also because the sine of n pi for integer n vanishes, here we would have sine of 4 pi, here we would have sine of 8 pi at the upper limits, they're also going to vanish. So the only thing that's going to survive in the limits is the 3/2 lambda when lambda is equal to pi. So we're going to have 3 over 2 times 4, so that's 3/8 times pi. So our integral is therefore going to be 3 pi over 8. And that is our result for the integral of cos to the 4th of 2 lambda with respect to lambda. So the key thing to realize here was that this was an even power, and we used therefore double angle formulae, and we had in this example to use it twice. With that I will stop this video.